And we're back. Welcome back and happy Thursday. Today we're going to switch gears and we're going to talk a little bit more about Bayesian classifiers. Some administrative bits, the reading. We had this a little bit further back in our modules, and I trust by now that you've done this. If not, this material or some of it can be found in the first 48 pages of the Flat Machine Learning text in Chapter 1. So when we last met, we talked about a generative classifier, and we said we calculated the probability that Y is a certain class label given your input feature vector X. And we call this the posterior distribution over the class label. And then it's equal to, through Bayes' rule, probability of Y, our feature vector, given X, our feature vector, given Y, our class label, our data likelihood, times the prior distribution over class labels, probability of Y equals C, class C, over our normalization factor. And so we said that all of the items on the right-hand side of equality can be calculated from your data, and that gives you an expression for the posterior distribution over the class label. So one of the problems of modern life is the deluge of email, and in particular, a particularly bad problem is spam email. And so one of the solutions for dealing with spam, this illegitimate email, is a tool called Spam Assassin. It's quite popular, quite famous. But before we get into that, let me just go over what spam is. And so spam is a pork product that is packed in a can, and it is a mixture of chopped up parts of the pig, and it's collected together into a kind of loaf and put in a can, and there's a brand name called Spam. And this name Spam is also used to describe illegitimate email that is sent and populating your inbox. And spam can be all sorts of things, such as advertisements for pharmacies, for all kinds of things. So-called junk email is called often spam. So on the left-hand side, this is a can of spam, and I believe you can still buy this now in the supermarket. I've only had it once in my life. Some people like it. It wasn't my thing. But there is spam, and if you take it out of the can, it comes in the shape of the can, and you slice it. Some people slice it and make sandwiches. Some people cook it and make a meal out of it. And this is what it looks like when it's sliced. Now, in contrast to spam, there's ham. Ham is the hindquarter here of the pig, and this is what it looks like in real life. And you bake it. Some people roast it. Some people boil it even, and then you slice it and eat it in sandwiches or sometimes as part of an entree. And so spam is the term used for illegitimate junk email, and ham is the term used for things that are not spam. Okay, so now we've established what is spam and what is ham. And so this is a page from Spam Assassin, and it's a configuration document or feature document that talks about what Spam Assassin is. It's the #1 open source anti-spam platform, and how it works is you, as an administrator, system administrator, you install it, and you define a number of rules that this Spam Assassin has, and this rules match for certain patterns in the email text. And so the Spam Assassin would be some plugin or add-on to your email server, and it runs these rules over the emails that come into the email server, and based on the rules that are true when they're run over the email, it sets a number of variables, returns some values. Okay, And so here's an example spam assassin report. And we see a bunch of these rules, and then we have a weight associated with each one. So, for example, is HTML included in the message? That's one rule. Is HTML font face not a word, right? So the font typeface. Does the email have an inline GIF file, right? That's a telltale indicator of spamminess, and that gets a weight of 1.4. And so in Spam Assassin, a series of tests is run. Each is associated with a score. Now, positive scores imply that this particular email is suspicious. Negative implies that it's non-suspicious. Suspicious means it's spam. Non-suspicious means it's ham. Now, if the total score associated with all the rules that fire and are run over an email is above 5, it's then marked as junk or as spam email. So you have this rule base, and all of the rules in this rule base are run over each email that comes in, and the cumulative score is used associated with each rule. The cumulative score associated with each rule is used to determine whether or not it is spam or it is ham, and it's typically associated with a threshold. So the total cumulative sum of all the rules, if it's 5 or more, then it is spam. Now, let's take a simplified example. Let's look at what these weights are. Suppose you have two tests, X1 and X2, and the outcomes of these tests will determine whether that particular document, that email, is spam or ham. And let's assume, for the sake of our consideration, that test X1 and X2 can take on one of two values, 0 or 1. And let's, for the sake of simplification, to describe the concept of what Spam Assassin does with these rules, you have a training set of size 4, and ground truth, the priors are such that you have 3 emails that are ground truth, that are ham, and 1 email that is spam. And so in this table, we have information corresponding to each one of the emails associated with our n many, where n equals 4, n many emails in our data set. So we have a data set of size 4, email 1, email 2, 3, and 4. In the next 2 columns, we have the outcome of the tests for X1 and X2. So X1 and X2, respectively, are 1 and 1 on the first email, 0 and 0 on the second email, 1 and 0 on the third email, 0 and 1 on the fourth email. And so spam, well, the first email is spam, and all the other emails, 2, 3, and 4, are ham. And so now what we want to do is come up with a formula, some linear combination or set of weights associated with our test X1 and X2, given that threshold of 5, that will work. And so X1 and X2 both will recognize spamminess, and the outputs of X1 and X2, if it's 0, 0, 1, 0, 0, 1, those are outputs on emails that are deemed as ham. And so we can solve from this for weights W1 and W2 using that idea of a threshold of 5, and having W1 equal 4 and weight W2 equal 4, that works. So that means this expression, 4 times the outcome of test X1 plus 4 times the outcome of test X2, that sum is a good way of combining X1 and X2 with weights W1, W2 equals 4 and 4, such that we know that this threshold greater than equal to 5 of determining spamminess holds. And so the learning problem consists of a weighted combination of each weight times each one of these tests, or you call these tests features, and we sum together that linear combination, W1 times X1 plus W2 times X2 for the first, the second, the third, up to and including the nth. Now, in this formula, we've assumed that we have more than 2. I'm just showing you for 2, but we're generalizing what this linear classifier is doing. And so we take that weighted sum or linear combination, and we add them up, the weights times the individual features, these indicator functions, and we check to see if they're greater than a threshold. And in this example from the previous slide, that threshold is equal to 5. And so in vector matrix notation, that's W transpose X. There's our linear combination, our sum. We're checking to see if W transpose X exceeds the threshold T. So now we can write W transpose X equals T. And if we look at this W transpose X equals T, that's nothing more than a decision boundary. And that decision boundary, if it were in two-dimensional feature space, where we have on one axis the first feature, the other axis the second feature, that decision boundary is a line on the plane separating the different points, where these points correspond to each email as described by its features x1 and x2. And so this decision boundary, if we take this expression, yes, our threshold is greater than T, but if we solve for W transpose X, so values X, for W transpose X equals T, we get this decision boundary. And that decision boundary, it's called decision boundary because it partitions our data as described by our features that are collectively 0 and 1, separates the spam points or emails from the ham points or emails. And so we can solve for this a little bit easier in practical terms, and we can introduce a new coefficient W naught. So you'll notice here in the original summation, we started at I equals 1 for the first feature, the first weight. And so if we introduce a W naught is equal to minus T, and an X naught dummy variable is equal to 1, now we can rewrite this expression as W transpose X greater than 0. And so if we rewrite this expression, that's literally taking W1, Wi, Xi, the sum, where I goes from 1 to n, and then we subtract T from both sides of the equality, minus T is greater than 0. So now if we cast minus T as W naught, that gives us our sum, I goes from 1 to n, Wi, Xi, plus W naught X naught is greater than 0. We can pull this term into the summation, giving us our new version of the index I goes from 0 to n of Wi Xi greater than 0. And now we have a new W. With that new W, it's vector valued. It includes W naught, W1, all the way up to and including Wn. And that now brings this expression to W transpose X greater than 0, where our X is X naught, X1, up to and including Xn. And so we can take our classifier, including this idea of a threshold, absorbing it into the summation, and now our decision is just checking to see if W transpose X is greater than 0. Now we can do this in something like MATLAB by checking the sign of it. Is it positive or negative? And that's sign W transpose X. If that is equal to +1, that means it's greater than 0. If it's -1, that means it's not greater than 0, it's less than 0. Okay, so we can certainly implement this, and we can now recast the decision boundary as being our augmented W transpose times our augmented X is equal to 0. And so this particular decision boundary you can think of as having an orientation and an intercept, or sometimes it's called a bias. And these are factors in choosing which linear model or line in the plane for 2 dimensions is going to be used to separate the points, the spam points from the ham points. Okay, and so we have our emails. We pass them through the tests in Spam Assassin, and this gives us our data. So you can think of this set of tests as our feature generation. And this feature generation recasts it in terms of these indicator functions, x0, x1, which can be 0 or 1, and that's now our data. Now, of course, our feature selection can be simple, can just be identity. And identity just says, okay, take all the raw features and use them as our representation. It's not a particularly good feature selection, but it is a feature selection to cast this system in terms of the pattern recognition pipeline we've been carrying all semester. So now we have our linear classifier consisting of a bunch of weights, and now given a set of training examples, we now learn the correct weights, W0, W1, from that threshold 5 example we had. That separates the classes well relative to the ground truth assignment of categories. And so our raw data is our email. Our feature generation is the email converted to data using these binary outcomes from the spam assassin test. And then our linear classifier, we run that. Okay. And so are there any limitations with this? Well, we said spam assassin relies on these rules. What happens when you need new rules? You also have to update the existing rules because maybe the types of words that spammers use will change. You also have to order the rules. Which rule do you run first, which you run second, when you execute them? What is the right order for execution of these rules? Are there rules that conflict with one another? If they do conflict, you have to resolve these conflicting rules. And if you have a growing rule base, it can be very difficult to manage over years and years and years adding to this rule base. And so there are a lot of limitations with this. Let's look at a Bayesian approach, and we're going to use a Bayesian classifier of the same sort that we talked about as a consequence of this Bayes rule that we described in the introduction. And so this is an example of a spam email that I had received, and it's some prescription health type of thing. And you notice here in the bottom, there's a lot of text. And this text is just somebody vomited on the page a bunch of text as part of the email. And I viewed it in webmail so I could look at the source code instead of a regular email reader client. And you have just jumble of words. And so this jumble of words is there to try to get past filters. And it was caught as being junk mail, and that was spam assassin working behind the scenes looking for features in this raw text that are indicative of spam. So an online pharmacy, another one. Mark Zuckerberg was emailing me. Of course, I don't think Mark Zuckerberg would be emailing me, but nonetheless, this is asking for you to use your credit card to pay for something. It's clearly a scam. It's spam, junk email. Again, this was caught by spam assassin. Okay, and so let's take a look at how the Bayesian perspective or probabilistic perspective might think of this. Now, we can treat each feature, that indicator 0 or 1, as a type of information source. And thusly, when we're trying to come up with a description of what it means to be a document, you're combining the information sources with respect to whether or not it's spam or ham. So there's some coupling between the information source and this category spam and the category ham. So we multiply together these different indicators, and check whether or not they're greater than 1. And as an information source, we're looking at the probability of spam given each one of these information sources, each feature. And so we express this as a ratio between the two conditional probabilities, probability of spam given feature I, xi, the indicator, divided by probability of ham given xi. So what we're calling a likelihood ratio is between the two alternatives, probability of spam given one indicator over the probability of ham given that same feature or indicator. Now, of course, as an indicator, remember when we talked about conditional probability, we said a conditional probability says, in light of new information, how does that probability proceed? And so if there is some coupling between the two, that means in the Venn diagram, we have two events, spam and xi. They share information. There's some linkage between them. If they were independent, we said a definition of independence means they're non-overlapping in the Venn diagram, and the probability of A given B, if they're independent, is equal just to probability of A. So knowing something about B gives you no extra information concerning A. And that's similar to talking about what is the information linkage between them. Do they share any information? Okay, so we have this idea of our indicator, our feature, as looking at the ratio between the spam alternative and our feature versus the ham alternative and our feature. And we look at this ratio. And so we can also not only take the ratio of the conditional likelihood, probability of spam given xi, probability of ham given xi, we can also do the same thing with the prior distribution. And so this prior distribution makes no assumption about the feature, but just looks at the two categories. And so you can call that the zeroth feature, is the prior for spam versus the prior for ham. So probability of spam over probability of ham. And so we take each one of these indicators, we multiply them together, and if that result is greater than 1, then we choose the spam alternative. Otherwise, we choose the ham alternative. All right. And so here, you notice we don't choose a fixed threshold. We're looking at the ratio between the two alternatives. With a threshold, one of the practical issues is why a threshold of 5? Maybe it's a threshold of 6. Maybe it's a threshold of 2. And what it's saying is that is the information coupling between spam and the features greater than the information coupling between ham and the features? And because we express it as a ratio, all we're concerned about is which one is bigger, not a particular threshold in terms of the strength of, is it a 5 or a 6 or a 7 and so forth. And so we don't use a fixed threshold. And also, the beauty of this approach is that if you have more training inputs, more data, you get more emails. Because it's the probability, you can easily update this probability. Okay. So at its base level, the word content in an email matter in determining whether or not a particular email document is spam or if it is ham. And so let's define x to be our variables. And these are the representations of words. And let's call our target variables y. And these are going to be our categories, our class labels, spam and ham. And we're going to generalize these probabilistic models. We're interested in modeling the relationship between our features, x, and our labels, y, our target variables. And so as we talked about in the anatomy of a learner, we had a bunch of components, some of which you don't control, the ones in red, and some of which you do control, the one in black. And we talked about this hypothesis set of candidate formulas, and we're trying to find some function that mimics the assignment of labels to features. And so we made an educated guess for our hypothesis set, and we hoped that our guess was suitable enough as a function to describe the relationship between features and targets, and selected the best one by search using our learning algorithm. And so a probability is a kind of function. It's a function over the set of all subsets of our inputs, our sigma algebra, all the observables, and the range of that function is on the closed interval between 0 and 1 on the real number line. And so x is known, our features, because we have our data, and we compute those features over our data. In the case of something like our spam detector, we can evaluate the word counts and pose those word counts, the presence of certain words, as a set of features. A certain feature, the ith feature, is 1 if a particular ith word exists in this email. Otherwise, it's 0. If it's the second word, then the second feature. Third word, the third feature, and so forth. And so our feature vectors are known because we can generate features from our training data, but our class label is not. And so what we're trying to compute then is this information coupling, our probability of a certain class label, spam or ham, given our feature vectors that we do know. And so one of the things we can do, suppose we had two features. One feature detects for the presence of the word Viagra in a spam email, and the other for the presence of word lottery in an email. And we have our class labels, Y, which is going to be spam or ham. And so here's an example data set consisting of 4 emails. And we have our indicators, X1 for Viagra, X2 for lottery. And we have the following probabilities of spam given Viagra and lottery setting, and ham given Viagra and lottery. And so here we have Viagra lottery 00, 01, 10, 11, meaning that the presence of Viagra is in this 4th email and the presence of lottery is in the 4th email. But on the first email, there's no occurrence of the word Viagra and no occurrence of the word lottery. And so these are the respective probabilities, and you'll notice if you sum across the rows, that's equal to 1, law of total probability. We have 2 alternatives, spam and ham, on this condition. You have 0.31, 31%, 0.69, 69%. You add them together, that's 100%. So they are, in fact, probabilities. So we see these different probabilities associated with our conditional distribution probability of y, our target, given each one of our feature vector instantiations for the different instantiations we have for features depicting the presence of the word Viagra and the presence of the word lottery. So the presence of lottery in an email doesn't mean as much to spamness as the presence of Viagra. So you notice here, whenever we have Viagra but not lottery, spam is 80%. But when we have the presence of lottery and not Viagra, spam is 65%. So that means Viagra has a stronger relationship to being spam than does the word or the presence of the word lottery. And so we can average our posterior distribution target given our feature vector, Viagra and lottery's presence. We can average this across all the entries for Viagra. And so we write probability of our label given just lottery is equal to the sum for all instantiations of Viagra, probability of Viagra given lottery. Okay. And so if you actually do out the math, it does work out mathematically. I'll save that, leave that to you to work that out now that you understand how conditional probabilities work in Bayes' rule, sum rule, and product rule. Okay, and so if we look at this instantiation, that's the probability of y given Viagra 0 and lottery times probability of Viagra 0 plus y given Viagra is 1 and lottery times probability of Viagra is 1. Okay, and so given that the probability of Viagra being present is equal to 0.1, and we just kind of gave that value as an example, if we were to compute this expression, well, that would just be probability of spam given lottery is 0.625. Okay, and so we can absolutely do that for spam, and if we did that for ham, well, law of total probability says it's just 1 minus 0.65, and therefore, for this case where the prior distribution for Viagra equals 1 was 10%, we get an alternative that spam given lottery is 62.5%. Okay. And so our generative classifier, we said, we have a posterior distribution over the class label, probability of y given some class or some target, that could be spam or ham in the example we gave. We have the data likelihood, probability of our data given our class label times probability of the class label. So our data likelihood we can compute over the data. We segregate out those training examples of a particular category, that's given category. Remember, conditional probability is a type of filtering probability. And then for what remains, when we set aside those of a particular class label or target value, we compute the probability of those feature vector instantiations. And likewise, the prior, we can count that. We just count how many examples we have of a particular label, and then we express that over the total number of examples we have, and that's our prior distribution over that particular class label. And this normalization factor we can absolutely compute from the data. All right, and so you can fit this class posterior. You can fit a probability function to your data, or you can calculate it by counting from your data. And so now you do this for each alternative. In the case of the spam classifier using our Bayesian approach, you say y equals spam, and you calculate it. Y equals ham, you can calculate it or use law of total probability, and then you choose as the output for your classifier whichever of these class labels has the largest value for the posterior distribution over the class label. And that is our so-called generative classifier. And so for the probabilistic model, we have our likelihood function. This describes what you have seen. You collect all the spam, all the ham, and compute probabilities of the variable instantiations for each group. The prior distribution, you describe proportions of the target variable outcomes, collect all spam, all ham, compute the proportions, and then y given x or posterior, you use Bayes' rule to compute this. Compute it for spam, compute it for ham, and select the label, or predict the label associated with the highest probability mass between the two. And so this is our probabilistic model. It's immensely useful and very powerful, and we will have an opportunity to look at this in an implementation. All right. So with that, that's all I had for today. As usual, please make sure you're looking through the reading. And as always, please stay healthy, stay safe, and I'll see you all on Tuesday.